Hello everybody and welcome back. Root Beer here with the 2000 Fermat paper, and we're going to take a look at question number 14. Alright, in the regular hexagon A, B, C, D, E, F, so the one we have shown over here, two of the diagonals FC and BD intersect at G. The ratio of the area of quadrilateral FEDG to the area of BCG is, okay. Now I like that they've shaded this because it gives us a little hint as to what to do. This triangle right here is going to be the same as this triangle right here. We can show that. The diagonal is going to split the angle here. We got a common side length. It's going to be a right angle here. We can pretty easily show that this shaded area is exactly what's missing from the lower half of the hexagon. Okay. And that gives us an idea. If we cut out this little piece, and that's the same as BGC, then we could cut out a similar piece here. And that would be part of the shaded area, the quadrilateral we're trying to talk about. And maybe we could carve up the resulting rectangle in some way. So I'll show you what I mean. So this will be we'll say it's a regular hexagon. I'm terrible at drawing regular figures, as I would say most people are by freehand. D, E, F, and let's not forget A up here, and let's make that B look like a B. So I would say it's clear that BCG and GDC are congruent. And if we were to drop this guy down here to H, actually just use the diagonal AE, we get the point H. We can make some nice little observations. BCG is congruent to DCG, and that's congruent to EFH. Okay. So we have a bunch of congruent triangles. Fantastic. Now, we have no idea what the side lengths are. Okay. So let's give a name to the side lengths. So let's say that AB equals BC equals CD equals DE equals EF equals FA. We'll call that side length X. So that's an X, that's an X, that's an X. Lots of X's everywhere. Alright. So what do I want to do with these X's? Actually, I don't want to change. Do I want to change color? Yeah. So what I'm going to do is I'm going to show that I can carve EHGG up into copies of these triangles as well. And what I'm going to do is I'm going to compare angles. So since it's the interior angle of a hexagon, AFE is 120 degrees. This is something most people should know. Now, FC, it's a diagonal that splits the whole thing right in half. So angle HFE is 1/2 of that, so it's 60 degrees. Okay, it's exactly 1/2. And that means so since triangle EFH is right angled, then that means that angle HEF is 90 minus 60, which is 30 degrees. Now this gives us a 30, 60, 90 triangle, which I'm actually going to write a little bigger so that people at home can see what I'm doing. "30, 60, 90 triangles have a very special property. Okay? If you have basically the side lengths have a ratio 1, root 3, and 2, and this comes up every once in a while on contests, so it's really important that you understand 30, 60, 90 triangles. Okay? And so if we know that this is a 30, 60, 90 triangle, and that HFE is our 60, well then that means then the length of HF is going to be 1/2 of x. It's x over 2. So we have x here. It's going to be twice this length. So this is going to be x over 2. Okay? But that means, if we grab the green one, we can split DE in half. And we'll have an x over 2 here, an x over 2 here. And we can split these guys in half, and they're going to have the same height as HE. Let's call this I and J. So we choose I on HG, J on ED as midpoints. Well, then we get a bunch of similar triangles. So triangle FHE is then congruent to triangle JEH congruent to triangle HIJ, which is congruent to triangle GIJ, and finally triangle JDG. And all of these are congruent to triangle CGB. Okay, and that's the triangle that we're trying to find the ratio of this quadrilateral to this triangle. Let's never lose sight of that. But then we have 1, 2, 3, 4, 5 copies of this triangle compared to this one triangle. So the area of FGDE is 5 copies of triangle CGB. And that means that the ratio is going to be 5 to 1. We have 5 copies of one triangle compared to a single triangle. 5 copies to 1 copy, it's going to be a ratio of 5 to 1. Okay, and if we look, our last one, E, 5 to 1. Okay, so that's question number 14. So there's probably a couple ways you could do this. You could probably figure out a little more about the triangle and find exactly a nice way to do that. But I really like this way because it really kept in the spirit of ratios. We didn't try and calculate this in terms of x and this in terms of x. We actually showed that it really is a ratio of 5 copies of one triangle to another triangle. And so I think that's the better way to do it. But of course, you could say, oh, this is x, and BGC is a 30, 60, 90 triangle, So we could probably figure out a formula for this. It's going to be x over 2 times the square root of 3x over 2. So it's going to be root 3x squared over 4. And then maybe try and figure out the area of this one and compare them that way. That's fine too. That really is. But I think it's really nice to do this 5 to 1. Okay. So as I say, that's question number 14. And join me in the next video for question number 15.